In this question, we get to look at the rotation of an element, not about the axis coming out of the screen or the board or the piece of paper that you might be working on. The rotation is about the x-axis. And so what we do here is draw this 2D representation in 3D with the original coordinate system. So x, y, and then z is coming out. So in this case, we have x coming to the right, y still going up, and z kind of coming out in this perspective. And then we perform the 90-degree rotation about the positive x-axis. So if you rotate about x, you're going to continue to be having essentially this x-like axis in line with x, and that's the x prime. And then what happens to y? Well, y ends up coming out of the front face with a 90-degree rotation. So you have y prime there. And what happened to the z? Well, the z also goes 90 degrees in rotation and comes out the bottom. So that's what's happening to the coordinate system. It's gone from x to x prime, the y coming out the top, coming to y prime out the front, the z that was coming out the front now coming out the bottom, and z prime. And the question is asking us to describe the state of stress in this new x prime, y prime, z prime coordinate system. Now, the nice thing about rotating about an axis by 90 degrees is the stresses do not change, but the way we refer to them does. In other words, this box, if it's rotated 90 degrees, or this element, right, it's still going to have these stresses, this purple one for the shear stress meeting in this corner, these normal stresses coming out the sides, these two sides, they're still all going to be there, but the reference, the coordinate system that we're using is different. So how do we describe this state of stress in the x prime, y prime, z prime coordinates? Let's go ahead and let's write out, okay, whoops, let's not do that. Let's see, we have sigma x prime equals what? Sigma y prime equals something. Sigma z prime equals something. And this is hard to write like this. Um, we have tau x prime y prime equals something. We'll have a tau x prime z prime equal to something, and we'll have a tau y prime z prime equal to something. Now, right now, we're just going to use kind of this think method to do these calculations, recognizing that since it's not an angle of rotation like 30 degrees, 25 degrees, whatever, it's just 90 degrees, that we can just look at this image and get the results. But after we use this think method, we're going to go into Python and do the calculation with rotation matrices and tensors. Okay? But here, let's just kind of take a look at what's happening. So originally, right, there was this 50 megapascals in the x direction, and x has now become x prime. There's still 50 megapascals in that x prime direction. So sigma x prime will be 50 megapascals still. The sigma y prime, okay, so sigma y is now, so this is y original, y prime's coming out this phase. So originally sigma y was the 100 megapascals, but now y prime's coming out of this phase. There's nothing coming out of this phase, so this is just going to be 0. Try to make that a little neater. That's hard. Sigma z prime, okay, so sigma z was originally coming out of this front face, but now it's coming out of the bottom, and Z prime has aligned with it the 100 megapascals. So we can go ahead and write that that's going to be 100 megapascals. Like that, okay? The tau x prime y prime. Okay, so now this is where it gets a little bit tricky. Well, let's look at the x prime face. All right, so that's this face here, or this face here, x prime, and in the y direction, okay? Or y prime direction, better said. In the y prime direction, that's now this coming out of the face. Well, there's no stress on, parallel to the face in the y prime direction, so that's just going to be 0. Let's go to the x prime z prime direction. Okay, so x prime, like this, z prime would be coming down like this, right? You see z prime? And yes, I do have a vector, a stress that is parallel to z prime, but it's going in the opposite direction. It's going up in the minus z prime direction. So that means that it's going to be minus the 10 megapascals. Okay, and we have now the final one, the y prime face. So here's the y prime face and the z prime direction. There's no stress acting on this face, so this is just going to be 0 as well. Okay. So the only, well, okay, the sigma x and x prime did not change from x, right? We can see that sigma x is 50, sigma x prime is now 50. Sigma y, well, sigma y prime is now 0 when it was 100 originally, megapascals. Sigma z prime has taken that 100 megapascals. Tau x prime y prime is now 0, whereas tau xy was 10 megapascals. We hadn't listed the other shear stresses, the xz and the yz, okay, in the original state, but they were 0. This was a 2D representation here, but we see now this tau x prime z prime is the minus 10 megapascals, and tau y prime z prime is equal to 0. Well, let's go ahead and talk a little bit about how we can perform this calculation mathematically using linear algebra. And you don't have to have taken linear algebra to, I think, understand what we're going to cover here briefly. But you can dig a little bit deeper into basic, maybe shouldn't say basic, but into matrix multiplication, which is really what we're doing, and some transposing of matrices. So let's talk about stress tensors and rotations. If we have a stress tensor, sigma, it's going to have 6 components, and we've talked about this before. It looks like this. So sigma x is in this location, tau xy, tau xz. The main diagonal is the normal stresses. The off-diagonal terms are the shear stresses. Now, we have what are called rotation matrices. So if you have a vector or a coordinate system, and this is sometimes where the confusion can arise in terms of whether these rotation matrices are the transpose of what you might find in one textbook or another textbook. So it's whether you're rotating a vector or you're rotating a coordinate system. We won't go into those details here, but these rotation matrices can be written for rotations about, say, the x-axis, the y-axis, or the z-axis. And then we can calculate the new sigma prime, okay, the state of stress in the new rotated element by performing this linear algebra equation. So sigma prime is equal to r times sigma times the transpose of r, okay? And And so if it's an X rotation, then you'd have Rx, sigma Rx transpose. If it's a Z rotation, you do use a Z matrix, and you can actually do compounds of these. Let's look at an example. If you were given sigma x equals 50 megapascals, sigma y equals 100 megapascals, and tau xy is equal to 0. So this is different than that question 4 that we just covered using a think method. You have a rotation about z, okay, that is 30 degrees. So this is a z rotation of 30 degrees. Okay, so we select the rotation matrix for z, that was from the previous page, and we can plug in theta equals 30 degrees to solve for these terms. And we have our original tensor representing the original state of stress at the 0-degree rotation. Okay, it's just the original tensor. And then so we populate it with 50, 100. There's no shear stress. And then we go about running this calculation. Sigma prime equals RZ, sigma RZ transpose. This is matrix multiplication. We can do this using Python, okay, and this implementation. And then we look at the matrix it spits out, and we map the sigma x prime, tau x prime, y prime, tau x prime, z prime, the sigma y prime, the sigma z prime, all to this resulting matrix. So now let's go ahead and implement this matrix multiplication for the problem at hand. And to do that, you or I, we can go to this session 17, and there's the Colab, which we used for question number 3, actually. So you could click on that, and I still have it open. We'll go over and let's make sure, yes, you've got to run the top. Okay, so it's been a while, so we run it anyway. So we'll run the top, and then we'll come down, okay, to this session, or this example 17.5. This was that example 17.5 and its implementation. I'm going to copy this. There's not a question 4, so I'm going to copy this cell. Copy cell, and I'm going to paste it, Control V down here. Where did I put it? Okay, yeah, I put it right there, that's fine. And just I'm going to put in, this is session 17, question 4. And now we need to put in the state of stress that was given. It's if we go back 50 and the x, 100 and the y, and then tau xy is equal to 10. So let's go ahead and put those in. Actually, we might be able to, maybe this will be a little bit easier for us. So we can kind of keep track of things. Sometimes this is not the way to do things, but let's see. So 50, 100, 10. So 50, 100, not sigma z, tau xy is 10 megapascals. Okay, and this is going to be the sigma. This is the original tensor describing stress, and I will just print it out. Then we're doing rotation about what? About the positive x-axis. Okay, so that is not what's in here. Right now we have a z rotation. So if we come back over here, we can look to find here is the x rotation matrix. So we'll go ahead and we'll come over here, and you see that's Rx right there. So that's the blue one. Well, there are 2 blue ones, but let's go ahead and we're going to change this to Rx, and this is going to become 1, 0, 0, this is going to become 0 cosine good, and then I'll do MP sine theta. Okay, that's fine. And then the last one is going to be minus NP dot sine theta. And this one will be NP cosine theta, just like that. Yeah, I think that's good. We can go ahead and print the Rx rotation matrix. And the result needs to be Rx dotted with sigma dotted with Rx, like this. Okay, and so we should be able to run it just like that. And let's take a look and see what we get. So this was our original tensor, 50, 10, 0, 10, 100, 0. Okay, good. This is our rotation matrix. Okay, that seems to be interesting. Oh, but look, this doesn't look right. These, like, we 50 stayed the same, like we were talking about, but there's some differences in there that don't seem to line up with what we stated. Let's just go back here. Right, we had written out what we thought using the think method, the sigma x prime, sigma y prime, and sigma z prime would be, and this matrix does not look right. And the reason is because the angle of rotation is not 90 degrees, it's 30 degrees from the previous problem. So now we put it in as 90, and we run it, and let's see what we get. We get the following. Okay, so maybe this is good. We can copy and paste it in here just to kind of see how we did. So if I come out of this, keep sure and put it there, and we'll make it nicer and smaller. Maybe not that nice. Okay, well, there, it'll cover up some stuff. All right, if we look, zoom here we go. Whoops, flip. Okay, swap. Good. All right, so here we go. This component right here, which one is this? This one is sigma x. This component over here is sigma or tau x prime y prime. This is actually sigma x prime, sorry. But sigma x and sigma x prime are the same. Do you see this is times 10 to the minus 6 right here? Or 10 to the minus 16, sorry. That's essentially 0. So this is just going to be 0. Look over here. This is the tau x prime z prime, and it's minus 10. Great. That's exactly what we want. So we can say that this is minus 10. Tau x prime z prime is equal to minus 10 megapascals. Okay? And then this off-diagonal term is the same as tau x prime y prime. Okay, look at this. 10 to the minus 31. This is going to be for sigma y prime. Okay, and so that sigma y prime, look, we said it was 0, so that checks out nicely. This component right here is that is going to be tau y prime z prime, and that's for our intents and purposes is also 0. So we have a tau y prime z prime equals 0, so that checks out. And down here, so we only had to do the top half, but we need to get this last one here. That component is the sigma z prime, and what's that? That's equal to 100. Okay, and that also checks out what we had here. So for this kind of simple case, we were able to just think about the answers because it was a 90-degree rotation. But for more complicated angles of rotation, it would be a good idea to use these tensors and that technique, and just showing that, at least with a simple case, they both agree. Well, I hope you have found this video helpful. Thank you.